Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figureoutable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do, but y'all, it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keeps students from being the mathematicians they can be.
Last week, we dove into a new series about a strategy that we both love and find so incredibly valuable in everyday life. It's the over strategy.
Dun,
We
dun, dun.
also shared a handy download that we think you will love. That model represents what it might look like to use this strategy. So if you want, you can pause the episode and go find that link now so that you can put a mental image in your mind and how you might use the over strategy for subtraction. You can find that link in the show notes or at mathisfigureoutable.com/over. Okay, so Pam, last week we tackled addition. Let's dive into subtraction.
Let's dive into subtraction with your favorite strategy, which, to be clear, might be becoming my favorite strategy.
Oh, all right.
Just maybe.
It's a good one.
Yeah, it's such a good one. And here's what's partly good about it. It's so good to work with, what's a good word? Neophyte? Is that a big word? Like new people, like anybody who's never thought about numbers before.
Yep.
If we do just a little over with them, all of a sudden they're like seeing things differently.
Sure.
And they're like big wide eyes and they're like, what? Like, this is a thing? We can do that? And I'm like, yeah, we can do that. And all of a sudden then we can begin like to dive in.
Yeah.
So diving into subtraction today with maybe our favorite strategy. I don't know if it's our favorite, but it's a super, super good one.
You can have it as a favorite also.
Favorite doesn't mean it's the only favorite, right? We can have multiple favorites.
Right.
Okay,
Sure.
That's important. Okay. So definitely one of my favorites. Absolutely. That's part of my work, right? Where I looked at the body of knowledge and said, if it's not about teaching kids the subtraction algorithm, what do kids need to know? What does anybody need to know to be able to solve any problem that's reasonable to solve that a calculator? And in that research, we decided what the major strategies are, the major relationships that we need to develop in order to be thinking additively about subtraction, really reasoning with subtraction. And the good news is the over strategy made the cut. The over strategy is one of those major important relationships that if kids own, they don't need any stupid algorithms. All right. So for today, let's start off with a problem. And we're going to ask you to solve it, listeners, and then pause the recording and come back and we'll do a problem string together and see if maybe it changes the way you might be thinking about that problem. So the problem is 8,201 subtract 1,987. Subtract 1987. So 8,201 subtract 1987. Pause the podcast, give it a solve, and then come on back and see what we're doing. All right, so you've taken a look at the problem, and let's do a problem string to see how maybe we could get your mind sort of pinging in a direction that's kind of over-ish. All right, so Kim, first problem.
Yep.
47 minus 10.
37.
37. What is 47 minus 9?
38.
Why?
Because back 10 was 37, but I don't need to go back as far. So not a whole 10. I just need to go back 9. So I have a pen in my hand, Pam. Is that weird?
Where's your pencil, Kim?
I don't know. I don't have one handy, but
To be clear, I have a pen in my hand.
I'm sure you do. So I actually, it's interesting for me because over subtracting, I think a little bit more than I have to think for over adding.
You have to engage a little more.
I do. So back 10 would be 38, and then I went.
Wait, back 10 was 30.
Yeah, 37, and then I added one more to get to 38.
But we're subtracting, so why are you adding?
Because subtract 10 was too much. So then I added one back on, so that the distance between my two numbers, 38 and 47, was only 9.
So I actually, as you were talking, I wrote a number line, and I started at 47, and I jumped back a jump of 10, and I labeled that 10, and landed on 37. And then when you said, but I didn't subtract as much, just 9, I drew a shorter jump of 9, and it was just one shorter than the 10. And I labeled that 9. And so then it's obvious to me that I would need to look at on the number line, what is just one to the right of that 37? Sure enough, that's 38. Yeah, because you didn't subtract as much. Cool. Next problem. How about if I gave you something like, oh my goodness, I have a standing desk, and let's say it wasn't locked. So it just began to stand up on me. Okay, I'm all right. Here, we're back to podcast land. Here we go. So how about 82 minus 20? 82 minus 20?
62.
62. And how about 82 minus 18?
It's going to be 2 more, so 64.
Why 2 more?
Because I'm not subtracting as much. I'm not subtracting 20. I'm only subtracting 18. So it's going to be 2 more than my original answer.
So that first problem, when you said 82 minus 20 is 62, then when you said comparing that to 82 minus 18, that's too much. You subtracted too much. And so when I look at that on the number line, 82 jump back 20, land on 62, that 20 is too big. It's too far. Yep. Way back there, too far. So I have to bump back up, and 62 and 2 is 64. And I know I'm kind of repeating what you did, but I'm trying to repeat it in a way so that our listeners can kind of see what I would be making visible on the board, what I'd be drawing on the board. And teachers, I would be doing that. So if I was doing this with a real student, because Kim is a fake student, if I was doing it with a real student, as the kid would be saying it, I would be drawing it. I wouldn't necessarily be repeating it, but I would be drawing it. It can land on this problem with me for just a second. So 82 minus 18, it's almost like I said to you, hey, you owe me $18. Give me $18. And you said, all I have is
a 20.
20.
I just got a $20 bill. Yeah.
Handed me a 20. And I said, oh man, then I got to give you back 2. Right? It's almost like you're like, not 18. I don't have 18. Here's 20. Ooh, then I'm going to have to give you back. Even though we're subtracting 18, I would have to give you back that 2 because we subtracted too much of the 20 to begin with.
Oh my gosh. You're making me think of playing Monopoly with my kids and how at a very young age, so Cooper's 3 years younger than Luke, and that happened all the time. Luke would say things like, I'm not counting out $18. Here's a 20. Give me change. And Cooper, very young, would say, I'm not giving you some of my money. And I can remember when he would start to go, oh, okay, I'm getting more. I'm giving you less back. I remember that very clearly.
Well, brilliant. Well done, Luke. And well done to support that idea and then can turn into over. Super.
Yeah.
Okay. Right. Next problem. How about 467 minus 200?
267. So
I've just drawn a number line with 467 on the right, and I've jumped back this big old jump of 200. And that is, you said that was 267. Is that correct?
Yep.
I'm pausing for just a second because I'm thinking about the problem string, and I'm wishing I would have tweaked it slightly. So maybe ask me that at the end. Okay. So the next problem is 467 minus 195. What do you got?
272.
And why?
I actually just built off of the problem. I had written 467. I made a jump back of 200. to get to 267. So at that point, instead of drawing something new, I just added 5 from 267 to get to 272. Just made a jump kind of forward of 5.
And you might have had to think about that 267 plus 3 to get to 270, and then 2 more to get to 272. Nice, but you just had to tack on that 5 because you subtracted a bit too much. 200 was too much. You only wanted to subtract 195. Cool. Nice. Next problem. How about 8,201 subtract 2,000?
6,201.
6,201. Next problem. 8,201 subtract 1,987. Oh, it almost makes me want to play a little I Have You Need.
So then I did the same thing as I did before. I used the problem that was already there, and I just added 13 to 6,201 to get to 6,214.
13. Kim, where'd that come from?
The distance between 2,000 and 1987 is just 13.
So you were supposed to subtract 1,987, but the previous problem had you subtracting too much. You subtracted over subtracted 2,000. So you had to give back that difference of 13. And you said 6,201 and 13 was 6,214. So that was our problem that we started the day with, was that 8,201 minus 1,987. It's not the only strategy you could have used. In fact, I'm sure some of our listeners out there might have used a constant difference strategy, which would have been a fine strategy. But we intentionally tried to get your brains going in such a way that it would ping for you to think about using that minus 2,000 to think about subtracting 1,987. Yeah?
Yep.
Yeah, cool. Anything else you want to say about that problem? Just curious.
No.
Yeah, I like that you thought. That's good. That's
it. Wondering if there's anything else I have to say about it.
Kim is thoughtful, y'all. We're a thoughtful pair. We like being thoughtful. All right, next problem. Wait, there's another problem? Oh, yeah, we're never done. How about 18.2 or 18 and 2/10 subtract 10?
8.2. 8 and 2/10.
Because you subtract off the 10 off that teen, and that just leaves you with the 8.2. Very nice. Or 8 and 2/10. Cool. Anybody want to guess the next problem? If we had 18.2 minus 10, how about a next problem of 18.2 minus 9.9?
8.3. Because 9 and 9/10 is only a 10th away from 10. So we subtracted a 10th too much. So I'm going to add the 10th back on to get 8.3.
And since the previous answer you had when you subtracted 10 was 8.2 or 8 and 2/10, one more 10th would be 8.3 or 8 and 3/10. Super cool. All right, y'all. So the over strategy with subtraction is a pretty nifty strategy. However, let's be really clear that with this strategy, it can be super tricky for students who it's not kind of a natural inclination. If I run into students who are already kind of playing with this idea of over subtracting, they kind of have this idea that they're subtracting too much. And so they need to kind of adjust by adding back. It's like when she gave me that $20 bill, but I only needed 18. We're going to have to give her $2 back. That idea, if you kind of have naturally been playing with it, seems to flow pretty well for kids. If you have not been naturally playing around with it already, it can actually be quite tricky for students because as they're subtracting, they think they just keep subtracting. So for example, when we did 47 minus 10 was 37. Then when students look at 47 minus 9, often they'll use that minus 10 to get to 37. And then they'll go back one more to 36. And then we'll have to ask, is that 47 minus 9? Should we get a smaller answer when we subtract less? Or should we get a bigger answer when we subtract less? And that is a complicated idea if you haven't ever been playing around with it. So we like problem strings like in the format that we just did with you, where we kind of give you that helper problem to use. And you can use it for the next problem. But boy, then we got to talk about it. We've got to really make sense of where that smaller jump is. If you over subtracted first, where is that tinier jump? If for 82 minus 20, if we subtracted that big old 20, where would that jump of 18 be? Would it be a bigger jump than 20? well, yeah, then we'd land behind the 82. But if it's a smaller jump than 20, 18 is smaller than 20, boy, we got to add back on to that answer we had when we over subtracted. Again, that can be
Yeah.
really tricky for students, but so much more figure outable if we make the thinking visible, put it up in
Yeah.
front of kids, draw those open number lines. One of my favorite things to do is to draw that first problem, the number line for the first problem, the helper problem. And then when we get to the second helper or the second problem, redraw the helper problem and then draw in a different color that shorter jump and make
Yeah.
sense of longer jump back, shorter jump back, and kind of have color help us sort of differentiate between the two jumps, and then help that sort of stand out and kind of be visible as participants are doing the problem string. As I do a problem string like this, you might find it noteworthy that for the first few problems in the problem string, I will model the helper problem. And as the student tells me how they did the harder problem, the clunker problem, I will redraw the helper problem and then put
Mm-hmm.
the clunker problem on that same number line. So now I have one number line with the helper problem and one number line with the helper problem and the clunker problem
Yep.
together. But I usually
Yep.
only do that for the first few problems. If it seems to be going well, now I work mostly with adults or older students. So this for younger students, the first time you see it, you're probably going to do that for every problem in the string as you go. With older students, that it's kind of going well, they're using the helper problem, it's making sense. Eventually, I sort of drop off redrawing the helper problem, and I just draw it once. I draw the model for the helper problem, and then on that same model, I go ahead and add back what needs to be adjusted because we were over subtracting. Does that make sense, Kim? Do we need to click?
Yes, and I'm
Why are you
laughing
laughing?
because
Don't laugh at me.
well, because I'm used to modeling the same way with students. And so on my paper, as I was solving problems, the first two sets, I made two separate number lines. And then I started doing the same thing where I just added back originally. So I'm laughing as you're describing because that's what
It's
I
a
do
thing.
too.
It's a thing. Yeah,
Yeah.
absolutely. So
Yep.
we've kind of gotten in this rhythm of that makes sense.
Yep.
Yeah, nice. All right,
Yep.
y'all. Hope you've enjoyed that problem string. Let's talk a little bit about the over strategy for subtraction and where it fits in the hierarchy with other
Yeah.
subtraction strategies. So we
Yep.
like to start with subtracting by a friendly number and subtracting to a friendly number first,
Mm-hmm.
where students are really messing with, like, so if it's a problem like 47 minus 9, that's not a good one to start with. If it was 82 minus 18, if that's the problem, then we would nudge students using problem strings to do 82 minus 10 and then adjust to subtract 8 more. That would be subtracting by a friendly number. And we would also sort of simultaneously work on things like 82 minus 2, subtracting
Mm-hmm.
to a friendly number, and then adjusting, then subtracting the rest of it that's left over. Those two strategies are
Yep.
about on par, subtracting a friendly number, subtracting to a friendly number. Once those are going fairly well, we've done a few strings for both of them. Students are creating those relationships, and the strategies are sort of becoming natural outcomes. Notice it's becoming. I didn't say anything about cinching and cementing and memorizing,
Sure.
not that. As that's happening, then then it would be a great time to bring in removing a friendly number over, where we subtract a bit
Yeah.
too much and then we have to adjust up, have to adjust
Mm-hmm.
back, like give back because we had subtracted too much. And then after that, we would also want to then help students parse out, when do you remove versus when do you find the difference? When does it make sense? When do the numbers call to you, sing to you, like make you ping in your head that you're like, I'm not removing for these numbers. I'm just finding how far apart they are. Or I'm not finding how far apart these are. I'm just going to remove that little second number. And so that would maybe come next after we kind of have done those three strategies. Then we would, the three being subtract to a friendly number, subtract a friendly number, kind of on par. Those are about the same. Subtract a friendly number over. And then we would work on this idea of difference versus removal, distance versus removal. And then lastly, the pinnacle strategy for subtraction, constant difference. We would wait until we had those other ones really solid, especially kind of difference versus removal. And then we would work on the idea of constant difference. So that's
Yeah.
kind of the hierarchy and how it falls out. If you'd like to see that, I just talked about it, but if you'd like to see it, you could totally download our free ebook, which we're really quite proud of. It gives a lot of information, not just about subtraction. You can find that at mathisfigureoutable.com/big.
Yeah.
mathisfigureoutable.com/big. Kim, I want to talk about one other thing, and I think I have time.
Yeah.
So another thing that is super helpful about developing the relationship so that the over strategy becomes this natural thing that kids do. Another thing that comes out, that pops out, that's so useful is place value, right?
Yes. Yes.
So as we look at this particular problem string, oh, and I didn't tell you in this episode, so it might be helpful in this episode, which is sort of already gone by, but in the next few episodes, to write down the problem string as we go, because then you can kind of look back at it. As we look at things like 47 minus 9, in order to decide what the friendly number is, I'm using place value. I'm not just
Mhm.
labeling places, but I'm actually using the place value. I'm going to grapple with what number is nice close to that. And then how does that relate to subtracting 9? Similarly with 82 minus 18, I have to think about, I could subtract 10 and then keep subtracting, but I could subtract 20. And notice I'm messing around with what are the closest tens to 18. I mean, that almost feels like a little bit of rounding, like we talked about in a recent
Mhm.
episode where we talked about rounding. So that's a natural outcome of using the over strategy. When I look at a problem like 467 minus 195, again, I'm sort of thinking about, how does 467 relate to 195? Like, what's happening with those numbers? Ooh, 195 is almost 200. A little bit of rounding, a little bit of, in fact, a lot of our listeners, Kim, on the rounding or the rounding episode, were saying things like, well, it really does depend. Well, this would be a great example where what if it was 467 minus 194? Well, ordinarily,
Mhm.
194 would round to 190. That's not
Yeah.
helpful in this problem, right? I
Sure.
would want to round it to 200 and then just adjust by 6 if I
Right.
subtracted 194. So it's a perfect example. Yes, we completely agree with you that rounding depends on the context. And in this context, I would absolutely want to round up to that nice 200. Again, this is an example of how students are messing with, dealing with, grappling with place value as they kind of learn the over strategy. To be clear, it's not about rote memorizing steps to perform to do the over strategy. No, no, no. It's about creating relationships in the learner's head so that when they see a problem like 18.2 minus 9.9, they say to themselves, what do I know? Well, 9.9, that's almost 10. I can subtract 10.
Yeah.
Woo! I just subtract that 10 and then just adjust that little bit because I subtracted a bit too much. So lots of nice place value can come out of, well, lots of things, but one of them being place value out of messing around, playing with, learning the over strategy. And today, particularly for subtraction.
Yeah. And you mentioned pulling thinking out of kids and helping to make it visual so that they have an understanding of what's actually happening.
Yeah.
And again, if you're interested to see what it might look like to model someone's thinking for the over strategy, you can check out the free download with a variety of examples on appropriate models. You can find that download at mathisfigureoutable.com/over.
And we're really finding that leaders in our support group are finding these downloads super handy to use with their
Yep.
teachers. Every time we talk to them, they're like, oh my gosh, love it, using it all the time. Super.
Yep. Yep.
All right, thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.